Hi everyone, welcome back. This is part C of our video, our second video in part C. And in this video, we'll take our circuit devices that we've made and we'll connect them using waveguides. And then we'll extend that further and try to create a circuit response from the whole circuit. So to recap what we did last time, we placed 4 grating couplers, and then we also placed the contradirectional coupler device, and we ensured that the devices were spaced out on the grating coupler side correctly. So in this video, what we'll do is we'll take our ports of each device and ask them to be connected with a waveguide. So what that will look like is the grating coupler has a port here, and our contradirectional coupler has 4 ports each, and we want to connect them to each respective grating coupler. So we can return back to our code here in the spec section, and then underneath the placement, we can now add a connectivity call. So what that looks like is I3, and we can call something called connect bend. So this will automatically create bends for you as necessary. We just have to pass to it the port names. So we can start with GC1, and GC1 has a port called the output port, or out. And then we want to connect that to our CDC port 1. And just with that, it'll automatically create the waveguide and bends. There are ways to specify further what waveguides, etc., or other connectivity options. Feel free to check out the IPKISS documentation online. It's very excellent, and there are a lot of examples in it. So we'll copy this 4 times for each of our grating couplers. So GC 2, 3, and 4, all the output ports, and then we'll connect them to our contradirectional coupler 1, 2, 3, and 4. And then we'll give it a look. And then here it's asking if I forgot a comma, and indeed I did. So we'll add a comma here to each of these lines. And then as best practice, I'll add one to the final one as well, so that the same issue doesn't come up again if I add more items. So here we should see that our contradirectional coupler will be connected to our grating couplers. And from a quick glance, it looks good. So we can take a look down here, and we can see that the grating coupler is connected nicely. And then here's our waveguide. And then if we check our contradirectional coupler, it connects nicely to our device. What you do want to be careful of is up here in port 3. So if we follow port 3, you'll see that a crossover actually happened. And the reasoning is because of the port naming. So if you recall in our previous videos, we set our ports to 1, 2, 3, and 4. What that looks like is this will be 1, 2, 3, and 4. Sorry, maybe I should rotate them the other way. So this would be 1, 2, 3 is here, and 4. However, our grating couplers are 1, 2, 3, and 4. So if we try to match this numerically, you'll see that the 3rd grating coupler is actually matched to the 4th port, is what you would want if you didn't want to overlap. But if we were to do what we just did and match 3 to 3, we'll get an overlap like this. And that's what we're seeing here. So just a small tip to check this whenever you generate these devices. There are other ways to check for this, but best to be aware that this could be an issue. So what we want to do is we want to update our ports and flip them. So GC3 is now connected to port 4, and GC4 is now connected to port 3 of the contradirectional coupler. And then we'll rerun our script, and we should see this issue be fixed. So everything looks like it's working well. We'll zoom in, and we'll see that now we no longer have that weird waveguide overlap. Everything looks good, and then we'll do a quick check of the connection area for the top side of the device, and it looks good. So from there, we've made our circuit very quick and simple and easy. Just a few easy declarations, a quick placement of the devices, and then a quick connection, and then we're good to go. Now let's say we want to take this further, and we want to create the circuit model. So before that, let's check our GDS while we're at it, just to be thorough. So you can see that our GDS are made as well. Connections look good here. There's no overlap on the top side. The connection is good here for the contradirectional coupler. And everything looks like it functioned properly. So we made a really fast, simple circuit. So coming back to doing a circuit model now. So in the same way that we did it for the advanced P-cell and the regular basic P-cell, we can also call the circuit model of the devices. And what's great about the circuit model of the whole circuit now is that you'll be able to connect all the S parameter files together so you get a realistic response of our device after it has gone through its inputs and outputs. So what I'll do here is I'll create a circuit model that will include the grading coupler, both the input and the output. And then what I'll do is I'll show the grading coupler's innate response, and then I'll show the contradirectional couplers. And then what we should see on the final plot where we have a circuit model of the whole thing is that we'll see our filter response on top of our grading coupler response. So to start off, let's create a section called circuit model, and then we'll import numpy. We're going to need it in a bit to declare a wavelength range for the S parameters. And then we'll also import Matplotlib .pyplot as plot, and that's just to plot the transmission in a bit. So using our numpy, we'll create a variable called wavelengths. It'll be a linspace of, let's say, 1.52 microns to 1.58 microns in wavelength, and we can give it 4,001 points. And then next we want to create the circuit model for the grading coupler. So the grading coupler here. So GC underscore CM for grading coupler circuit model. And then so the GC has a circuit model function like we made in our previous video. So if we look at our previous code, we also have a circuit model class over here. And then we can pass to it some parameters that we want. So what we want to do here is let's center the wavelength at 1.55 microns, the bandwidth of 1 dB is 0.03. So all these variables are actually in that grading coupler class, and then you can take a look either in the documentation or open up the actual P-cell to access what is there. So here we'll add some insertion loss just so we can see it. We'll add some reflection. Sorry, 0.5. And then we'll add a reflection for the vertical in as well. Just use some default known parameters. And that's good to go for the circuit model. So what we can do now is we can then create the S parameter for the circuit model. So I'll call it S underscore GC, just to keep the namings quick and dirty. So the S parameter can be accessed through GCCM, our circuit model for this device, and then we call get S matrix, and then we tell it the wavelength range. So we pass that wavelengths object over to it. And now that will generate the S parameter for that particular wavelength range. And then what we can do next is we can ask this S parameter object to be visualized. And then we'll have some pairs we have to declare to tell it what the ports are. So the variable is called term pairs. And we pass to it an array. And then in the array, the first, well, the only one in this case will be the vertical in as the input, and it'll go to the output. So just a simple single grading coupler response. And then what we want to do next is we can then showcase the CDC's circuit model and S parameter transmission. So we'll say contradirectional coupler. And then in the same way, we'll create an object for the circuit model. Circuit model. And we don't have to pass anything here, where you can just leave as a default to keep things easy. And then the wavelengths, we can pass the same one really. We don't have to declare more here. So let's just delete that. And then we'll create the S parameter object for the CDC now. CDC underscore CM dot get S matrix. And then we'll pass in the wavelengths as well. And then we'll also visualize this just so we can see the device by itself before it gets compounded onto the grading couplers. So visualize, and then we have term pairs. Okay. And then here we have 2 because it's a 4-port device. So we'll take port 1, and then it'll go to port 2. So this should give us our 2-1 response, which should be our drop port. And then we'll also get our port 1 to our port 3, our throughput response. And with that, I think we are good. So we can save here. Let's see if we wrote anything wrong. Yes, we have a typo. Not term pairs, term pairs. And I think that should work. I'm not sure why it's giving me a warning here. Let me check my other copy of the code real quick. It looks correct to me. So let's keep it for now, and we'll deal with it when it comes. And then finally, we're gonna get the circuit model of the full circuit. So here we'll do full circuit. And then what this will look like is we'll create the same thing. So my circuit now has a circuit model, or circuit model object, I should say, which is called from the circuit model function. And then we'll call it S circuit for the total circuit. And this will be my circuit.cm or underscore cm get S matrix. And then we'll pass it the wavelengths. So overall, nothing too fancy argument wise. We can just keep reusing the same arguments. Then a circuit will be visualized. And then our term pairs this time. We'll have port 1 go to port 2. So keep in mind, this port 1 here is now referring to this exposed port name that we've put out because it is a circuit. It is not pointing to the individual device instances we have. So that's why it's very important for us to create this exposed port name list up here. So we'll get the S21 essentially, and S31 as well, since it's a 4-port device. So port 1 to port 3, no spaces. Oh, sorry, it should be port 4. And if you recall why, it's because in the previous video we flipped our ports. So we actually want to see port 4 that is going to go to, so we want to see port 3 of our CDC, which now exists on port 4. It needs a black pin. So we actually want to see this, which would be a throughput port, and it's actually going to port 4 and not port 3. So here we'll put port 4, and then this will be S31. And then with all that done, we should be able to run the whole thing, and we can deal with the errors if there are any. So let me close the other file, and then let's give it a run. So string object not callable. Did I miss a comma? Yes, I did. It's another comma issue. Messed up there. Okay, so it seems like it ran, but I didn't call it to run, so let's rerun it again just to make sure it's not doing some weird error. So let me stop the whole thing and I'll run it again. So we should see this time our transmission, and it should show the grading coupler first, which would be a Gaussian curve, like so. That's excellent, and it's centered around 1.55, like we asked. And what's great in IPKISS is because we label the ports, they also give us what the curve of the ports are. So in this case, we asked for the vertical in to the vertical out, and this is what it looks like here, labeled in blue. And then we added our insertion losses, so it puts it about 0.9-ish. Next, we should see our contradirectional coupler. So again, we should see some filter response. Oh, sorry, I typed it wrong. It's term pairs, not terms pair. So here we'll rerun it again, and we'll get to that filter response. The filter response should just be the same as we expected and saw in the previous part B. So nothing fancy. It's reading from that S parameter file. And you'll see it's a bit off here. The reasoning is because it's extrapolating because we gave it more points. There's an easy fix to this, and I'll showcase it in a bit, just so we can make sure that the transmission is proper and reasonable. But this also comes because our simulation didn't put enough wavelength points into it, while we're asking for a higher amount of wavelength points. So we see an error here for the term pairs for the final one, so we can check that as well. But we'll solve that contradirectional coupler issue first. So the solve is quite simple. Right before we pass a wavelength object, let's overwrite it, and let's give it a new amount. Or rather, we can do the same thing. We can just update the one up here instead. So let's just go update the original. And we'll update it to 1.5 to 1.6, and then it'll be 201 points in line with our S parameter that we generated. And then next, let me check what this issue is with the term pairs. Too many values to unpack. Let me see if I type something wrong. Yes, I missed a quotation mark. So I actually passed the full string when I actually wanted to instead pass two strings separately. So that looks good. The error is gone now. We'll space it out so it's more readable. And that should fix all of our errors. So here we'll run it once more, and we should be able to see everything. There's our new grading coupler response. And then here our contradirectional coupler is looking more reasonable now because we're using the amount of wavelength spacing that we simulated with. And then now we should see the full circuit transmission. So we can see that in the orange here, overall the envelope does show the grading coupler's insertion response. And then we do see that filter response overlaid on top of it. So overall, it looks like it worked correctly and simulated our full circuit model. And you can see here that our ports are also labeled here. So port 1 to port 2, this is our drop port, which is the filtered out signal. It looks correct. And then port 1 to port 4, that's our throughput. Port 4 in quotations, of course. It's actually grading coupler 4. And it's our throughput signal with that response filtered out. So overall, everything worked correctly. And then what we can do next is disable this circuit model part first. We don't need it anymore. But also showcase the final thing before we end off, and that's exporting to IPKISS Canvas. So here we'll do a section for to IPKISS Canvas. So there's a lot of options you have available. You can use numerical interconnect and create the circuit model manually. All the S parameter files are there. Or you can export everything you have directly to IPKISS Canvas. And there's a really nifty little function you can call called toCanvas. And all you have to do is give it a project name. You can name it anything. So we'll call it test circuit. Let's see if I spelled project name correctly. Yes, I just added a extra parentheses. That's why there's an error. Okay, so with that, we now can execute the code and it should pop up our IPKISS Canvas for us and recreate the exact same circuit we described. And then finally, we can also compare it to the GDS file. So here I launched IPKISS Canvas, and right off the bat you can see our grading coupler. We'll have to zoom out quite a bit, and the reasoning is because we used our own units. So you can fix this by using different units. But here we can see that IPKISS Canvas also conveniently added for us a waveguide object here as it moves on to connect to our contradirectional coupler object here. And then just like our layout, it then goes back out to our other grading coupler ports. So a quick and easy way to go directly from a script into a circuit model, or if you want, it can also go into your GDS layout. So here you have our GDS layout. And it's quite fast in my opinion and very easy to use, just for a designer to go directly from your scripts and then existing P-cell modules you might have. Basically just starting to instantiate them, only a few lines of code, one for each device essentially, telling it how many instances. You can even probably write a for loop here to add these if it's a really big project, and then connecting them as such. So there's really a lot of room for customization as well, and it keeps things very easy. The parameters I think are very straightforward as well. But yeah, that brings us to the end of this video. It's quite long. But I also wanted to mention that if there's any questions or curiosity or support needed, the team at Luceda is very good at handling all these questions. Feel free to reach out to them. If there's any numerical related items, feel free to email us at oursupport@simutech.com. But yeah, you can find the Luceda support at their website. So if you go to Luceda Photonics, and then navigate over to support here or services, you can click contact them, and they have excellent customer service. They're always happy to help out, especially with anything related to IPKISS as well. And then of course our Simutech support email with any ANSYS related issues. But yeah, thanks for watching. Take care everyone.